So today we will explore different ways to make performance measurements on the Adafruit Metro M0 Express board. For this experiment, we will be using the AES 256 and Chacha20 cryptographic algorithms to encrypt and decrypt 1 megabit data as benchmarks. After running and verifying the benchmark codes on the board, we will measure benchmark timing using I/O pins and an oscilloscope. That is, we will be probing the LED pin before and after the encryption and the decryption runs. Following that, we will also demonstrate the usage of UART to print the timing data that we measured. Finally, once we have the timing data, we will measure the energy consumption of our microcontroller while running these benchmarks. To measure the energy, we will connect a sense resistor in between the microcontroller and our power source and measure the voltage across the resistor to calculate the current using the Ohm's law and ultimately calculate the energy in joules using the formula power into time. Now to give an overview of the benchmark, this code combines both the Chacha20 and the AES cryptographic algorithms. To enable one of these algorithms, we need to uncomment the macro one of the macros and comment the other macro that is not in use. So here we have commented the Chacha20 macro so that we are using only the AES and the AES code is enabled in this code for running on the microcontroller. Now, in the AES 256 code, we are using the tiny AES library and including the necessary library files from that folder. Further, we define a CTX object of the AES CTX struct and define the key size as 256 since we are using the 256-bit key. Now this is defined in the test.h file where we have commented 128 and 192-bit AES and just kept the AES 256 enabled. After that, we have defined two functions, the encryption function and the decryption function. So the test encrypt function basically has two parts. The first one is the Chacha20 encryption function and the second is the AES encryption function. By enabling the macros, we can disable the other part of the code when we call this function. So in the test encrypt function for the tiny AES, we are using the AES encrypt function where we pass the plain text and the uh, object of the AES struct. Similar is the code for the test decrypt function. Then we have two more functions to check the to verify our encryption and the decryption. So for that, we have the check encrypt function, which also again has two parts for the one for the Chacha and one for the AES, where we use the memory compare function to compare the expected CT, which is where our expected ciphertext is stored, with the CT, where our ciphertext, which is calculated from the plain text, is stored. And if the comparison value returns 0, then this function will return 1, stating that the verification is correct. The similar function is written for the check decrypt function. Then we have in our void setup, we just set the pin mode of pin number 13, which is our LED pin, to output so that we can use it for toggling and measuring the time. And then we use the serial.begin and set the baud rate to 9600 for our UART functionality. In the void loop, we are initializing three variables: start, finished, elapsed, to measure the time and finally print the time on UART. Then we are using the digital write function to write high on the pin number 13, and we use the micros function, which basically returns the uh, microseconds that have been passed since the board started running, and then we store that value in the variable start. Once this all is done, we start our encryption or the decryption process. Now here I have commented the encryption and just running the decryption test function for 100 and 1125 times. Now this is so because as I'll be explaining further, the data that I'm using for Chacha20 is 114 bytes, and the data I'm using for AES is 112 bytes. And so these number of bytes multiplied by 1125 will give me 1 megabit of data. So I am looping this data to get 1 megabit to encrypt or decrypt 1 megabit of data inside this loop. And once the encryption and decryption of this of our data is done, I store the microseconds that have passed in another variable finished, and I also turn off the LED by setting it to low using the digital write function, and then I calculate the difference between the finish and the start, which are the microseconds between the code running, and store it in elapsed. Now I use a serial print function to print the elapsed time, so that now we know, so that we can see the measured time in the UART console. Now looking at the data for AES, we are setting a 32 bytes array for making the 256-bit key. Then we are using the expected PT, expected CT, PT, and CT as the plain text and the ciphertext, which is 112 bytes in this case. Similar is the functionality for Chacha20 in the code. We can just comment the AES code and uncomment the Chacha20 macro to enable the Chacha20 part of the code. Here we are using the portable 8439 library and including all the necessary libraries and the files that are required for enabling Chacha20. Then we are setting the max test size to 512 bytes and creating a Chacha test vector structure, which takes the title, the key, nonce, counter, plaintext, ciphertext, and the size as the input. And here we set the 16-byte data as the key, the 12-byte data as the nonce, the 4-byte data as the counter, and then we have the plain text and the ciphertext of the size 114. And rest of the code is same as the AES. And now when we call the encrypt function, we now the it will call the Chacha20 encryption function instead of the AES encryption function. Now we look at the hardware connections that we need to do to measure the time using picoscope. So we have our Metro M0 Express board with the LED toggling code uploaded on it. So we have an LED connected to pin number 13, which is this pin shown as which goes to the GPIO. So we use a BNC cable connected to the our picometer, our picoscope. This picoscope is connected to our laptop via the USB, and we have our picoscope app installed on our system. So once we connect the picoscope, we connect one end of the picoscope to one end of the BNC of the picoscope to the GPIO pin, which is the pin number 13 in this case, and we connect the other pin to the ground of the board, which is also connected to the LED's ground. So after doing this and after running the code, we get the output as such on our Picoscope 7 app. We can use now in our Picoscope app, we can set the time per divisions according to the time that we are getting. So I have set my time per divisions scale to 100 milliseconds per division, and then I have set the amplitude to plus or minus 2 volts per division, and I am using the trigger option to basically stop the screen from running when a falling edge occurs. So as soon as this edge occurs, the screen is stopped, as we can see here. After that, I use the rulers option in the Picoscope application to adjust these two vertical rulers at the rising edge and the falling edge of the waveform. And as we can see in this rulers dialog box, we get the delta in milliseconds. So this delta represents the time taken by our code to run, which is 625.1 milliseconds. So in this way, we by toggling the LED on and off or toggling the GPIO before and after the um, our encryption or the decryption code, we can measure the time taken by the code to run using the GPIO toggling and the picoscope function. Now the next setup we need to do is for the energy measurement using the sense resistor. To measure the energy, we need to use a sense resistor in between a power source of 3.3 volt and our Metro M0 Express power pin. So we connect the positive pin of the power supply to our sense resistor, which is approximately 10 ohms here, and then we connect the other end of the resistor to our input of the Metro M0 Express board, and we short the grounds of the power supply and the our Metro M0 board. Then we use a multimeter which can measure voltage across the sense resistor and connect this on both the sides of the resistor. Now when our code is running, some average current will continuously flow through this circuit, and this current will cause a voltage drop across our sense resistor. So in this case, suppose the current is 10 milliamperes and the resistor value is 10 ohms. So we will see that the voltage across this will be 10 to 10, which is 100 millivolts. So when I took the readings uh, with 10 ohm resistor, I got a voltage drop of 177 to 178 millivolts across the sense resistor for for running the tiny AES encryption and the decryption code, and I got a voltage drop of 181 millivolts when I ran the Chacha20 encryption and decryption codes. So by dividing this voltage by the resistor value, I get the current as V by R. So 181 by 10, I get 18, and then our source voltage was 3.3 volts. So I calculate the energy using the formula power into time, or V square, and power is V square R or VIT. So I multiply 3.3 by the milliampere current and the microseconds time that I measured using the UART or the LED toggle. So here 276 is actually 276 milliseconds, which is similar to the 274 uh, 274 milliseconds above. So in this way, by multiplying all these values, we get the energy as 0.0164 joules, which is the energy consumption of the board when we run the test encryption function of the Chacha20 code. So in this way, we can measure the energy using a sense resistor and get the power consumption of the board. Now we compile our code and we will upload our code in the on the board using the USB cable. And once the code is uploaded, we open our serial monitor and we can see the elapsed time printed on the console. So 270, this is in microseconds, so 275 milliseconds have passed. This is the amount of time that it takes for the encryption or the decryption function to run. So this is how we get the UART reading. We get the timing readings using UART.
Now we will upload the code which has the digital write to the GPIO pin. To measure the time using the GPIO toggle, we upload the code to our board and then we open our Picoscope 7 app. We set the parameters as I explained before. We set the time division to 50 milliseconds and so that we can measure the expected time correctly. Then we set the trigger by clicking on the trigger and change the type to falling edge and single mode so that whenever the LED turns off, our screen will stop running and we get the correct values. Now I'll just turn off the rulers and we start running our application so that we can measure the real-time values. And now the trigger has been triggered, so we have this waveform in front of us. This is basically the toggling of the LED on and off. Now we use the rulers and set the rulers at the rising and the falling edge to measure the time difference between the toggling of the LED. And now we can see in the rulers dialog box that 276 milliseconds is the delta between the two rulers. So this is how we use the picoscope to analyze the waveform of the toggling of the LEDs, and we have successfully measured the time using the picoscope and the GPIO on our Metro board, and using the energy measuring setup, we also measure the current and just do the multiplication and get the readings as shown in the previous slides.